All right. Hello, everybody. Welcome to, well, I think the beginning of a number of talks about coroutines. This one is C++20's coroutines for beginners. I'm Andreas Fertig. I work as a trainer and consultant for C++, and I wrote a couple of books about C++ as well, and I'm the author of the tool called C++ Inside, which you might know, but in today's session, we will not use it, at least not as planned. Yeah, there are other talks about coroutines at CppCon. It seems that coroutines are the real thing now, finally. And I can simply recommend you checking them out if you haven't already put them on your schedule. Phil Nash does a talk called C++ 20 coroutines from the scratch. So we both have the same aim and focus here to start teaching coroutines from the beginning, but it's for sure interesting seeing two different people approaching that same topic with the same idea behind. It will turn out differently. There's a talk about generators in C++ for coroutines and a lot of other things. So go and check them out. That's yeah, it's really great to see the progress at this point. But let's dive into my session. Coroutines for beginners. That means I don't expect you to have any knowledge about coroutines, okay? That means we start real simple at this point. So here we have an overview comparing normal functions to coroutines. On the left, we have the normal function, which we are used to. And the call flow here is very simple. Our caller places a call to a function. That function then executes the instruction necessary, and at some point it returns control back to the caller. Nice and easy. And after that, the caller continues. Okay, we don't have any threads here or multi-threading at this point. This is the usual control flow. The function gets started and it returns, and by that, it's finished. Now, coroutines, on the other hand, work differently. On the right, you see that when a caller calls a coroutine can execute a number of instructions and then decide to suspend, because coroutines are suspendable and resumable functions. And coroutines can suspend themselves by either saying co-yield or co-wait. Both are elements we will see later. Okay, and once the coroutine decides to suspend at a point, it gives control back to the caller. And this allows the caller to execute other instructions and at some point resume the coroutine. That step can be skipped if the caller decides that it doesn't need any more information out of the coroutine. Well, it can decide to not resume it. Well, let's assume the caller resumes the coroutine, then the coroutine runs for another couple of instructions and may decide once again to suspend itself, giving once again control back to the caller. Caller now continues with its own instructions and then resumes the coroutine once more. And this can be a point where the coroutine then finally decides that it now reaches a state where it ends like a function. So it uses coreturn to give control back to the caller. Okay, so this is the control flow and the difference between functions and coroutines. And the power of coroutines is in that ability to be paused and resumed. And then we have, thanks to co-yield and the co-wait and the co-return, the ability to pass data into a running coroutine or get data out from a running coroutine. And as you can see from this figure here, the nice thing is that the coroutine decides when it suspends. And that means we don't need locks like in multi-threading with multitasking, where functions get interrupted because another thread now continues. So our data is under our own control, and that makes coroutines nice for cooperative multitasking, which we'll see an example later. So coroutines itself are nothing new. The term has been well established in computer science and it was first coined by Melvin Conway in 1958. It was only C++ who, well, took its time to finally implement them in C++. You've seen in the figure that coroutines can be paused and resumed, and that implies that they carry some state. They need information at which point to resume and what the data was on, for example, on the stack, all the variables, what the values they contain before the coroutine went to sleep, and restoring that once the coroutine gets resumed. And this data needs to be stored somewhere. It's in the so-called coroutine frame, and we have two different ways to store coroutines among programming languages. One is stack full coroutines, and the other one is stackless. And C++ implements stackless. So that means that coroutines don't use the stack to store this coroutine frame, this information. It uses the heap. So this is also something interesting to know at this point. And when it comes to coroutines, we are talking about cooperative multitasking, things that we can implement. I know them a lot from embedded systems where they cooperate with each other, the tasks give up and get continued, as opposed to having a real multi-threaded world where the scheduler from the outside pauses your thread and continues another one, or things like that, which often makes implementations more complicated because you all the time have to be aware that some data must be guarded because we can be interrupted at this point, or we are about to write to an external driver and we can be interrupted at this point. So this is much nicer to implement using coroutines. That means coroutines can really simplify our code at this point. Aside from now the multi-threading part, in some occasions, coroutines can help us to replace function pointers, so callbacks, because we can suspend them and resume them later and get information out. This is exactly what a coroutine does. And this is exactly what a function pointer does at the same point. Parsers are much more readable using coroutines because, once again, they can be suspended and resumed, and the state is automatically maintained by the compiler, by the coroutine. We don't have to add a lot of these state bookkeeping stuff around. So that makes them real nice, okay? So theory is so far, sorry. Oh, by the way, I did forget to mention that if you have any questions, feel free to use the Q&A and then post your question there, and I will answer them at a certain point. And I also plan to have some time at the end reserved for Q&A. So how do we interact with coroutines? We haven't seen one yet, and then we will reach that point soon. But how do we interact with them? We have 3 new keywords in C++ allowing us to interact with coroutines. And that's coyield, coreturn, and coawait. While coyield and coreturn both output something from the coroutine, they are different in the state they are leaving the coroutine in. So coyield means the coroutine gets suspended. That means we can resume it later. While on the other hand, as the return here in coreturn implies, that coroutine is finished. So we are not supposed to resume this coroutine again. In fact, it's undefined behavior if we do so. And then we have the third new keyword, coawait, and that's for input. So this is comparable to if we call a function, we pass parameters. But if we call a coroutine, we can only pass parameters at the beginning, right? And what is if we in between need to feed some data into the coroutine, like calling it again? And this is what coawait is for. So with coawait, the coroutine can pause and can say, hey, I need more data from the outside. Please tell me what to do. And then the coroutine is like coyield in a suspended state and can, of course, be continued, resumed, because that's the purpose at this point. Okay. So these are the 3 new keywords you got in C++. And because keywords are hard to find thing, we have to live with the co_ thing here, because a couple of these keywords were already used without the co in front of them. And we wouldn't want to risk breaking somebody's code at this point. So what are the elements of a coroutine? In C++, a coroutine consists of at least two things, sometimes even more. The first thing is a wrapper type. And this is the return type of the coroutine's functions prototype. Okay, if a coroutine, if you write, we will see that in a minute, write a signature for a coroutine, it looks like a regular function. And that one comes with a return type. And this is more or less a wrapper type. And with this type, we can control the coroutine from the outside. And for example, resume the coroutine, because we need some way to do this, or get data out from the coroutine as well as passing data into the coroutine. And this is basically done by storing a so-called handle to the coroutine, more or less a function pointer, which knows how to invoke functions like resume, for example. And inside this wrapper type, the compiler looks for a type with the exact name promise type. This exact spelling is on the slide. So this is a hard-coded thing the compiler looks for in our wrapper type, and it must be there, otherwise it's an invalid coroutine. So, and inside this, this type allows us to now control the coroutine more from the inside point of view. So the promise type we define, that can either be a type alias or type def to a real type, then it has only to carry the name promise type in the type def or in the alias. Or we can, of course, define this wrapper type directly, this promise type directly in the wrapper type. That's possible as well. And then we have to give it the exact same name. Okay, so these are the two main things a coroutine requires, at least. And then we have two optional items. We can have an awaitable type, which comes into play when we use co-wait. And we wait for something in the coroutine, then this operator co-wait, or this keyword co-wait, comes into play. And then we have another part which we often want to have when it comes to coroutines, and that's an iterator. If you remember back the figure I showed you in the beginning, a coroutine can be suspended and resumed, suspended and resumed, suspended and resumed, and so forth. And so this looks awfully like something you want to do in a loop. Resuming, suspending, right? And to make that machinery on the outside nicer, we can write ourselves an iterator around all that, which is something we will also see. So the key behind all this is a coroutine in C++ is a finite state machine, which can be controlled and customized by the promise type. We have a lot of customization options, which makes these kind of talks I'm doing now and all my other friends and colleagues do are so hard, because there's plenty of room for doing things differently and adjusting them to exactly your needs. That makes them real powerful in C++, but it means that we also have to do more implementation-wise than we have to do in other languages. Okay, so that, yeah, it's yin and yang. And we can go for the real efficient version here, but if we want a cheap and easy one, we still have to implement a lot of these things, you will see. The actual coroutine function, then, which uses co-yield, co-wait, or co-return, is the thing that runs and uses the three keywords for the communication with the outside world. Okay, it suspends by co-yield and co-wait, and it exits by co-return. So this is the communication channel inside or outside this coroutine thing, which for now is maybe more an abstract idea. All right, enough about theory. One item here, a disclaimer, I thought I have to put it on a slide. So please note, I tried to keep the code you will see as simple as possible, focusing on coroutines only. Okay, in production code, I work with much more public-private as well as potential getters and setters. But I ran out of screen space real quick, and some of that may obfuscate in the brief time we have here the reading. Okay, so in addition, I would use way more generic code in production. So a lot of these things we are seeing now, they yell templates to me to keep the repetition slow, to have the reusability and all that, but I decided also to remove the template part because it distracts here and makes reading and harder and the following for this talk. But the goal here is to help you understand coroutines, and I'm real confident that you can improve the code you will see using the usual C++ best practices. Okay, I have no doubt about that. There's one teeny tiny bit. I also really, believe me, never declare more than one variable per line, except in slide code. That's the only exception. So apologies for that. Don't do that at home. Okay. So let's start with our first coroutine at this point. I have in line number 1 a function called fun, and that one returns an object called chat. And now I can see inside the function's body here in line number 3, 5, and 7, I have the co-yield, the co-wait, and the co-return. So that means one of them is enough to see that's a coroutine. And that means chat here, also in A, that's my wrapper type. And it must contain such a promise type as I told you about before. And then my co-yield here that yields a std string. So that means it reaches inside a promise type, which we'll see next, and calls a function there yield value. So we have a transformation here from the code we see to what the compiler does behind our backs. And then in line number 5, the co-wait does the same thing. It reaches into the promise type, therefore a function called wait transform, waiting for a result. And then in line number 7, my co-return here reaches into the promise type for a function called return value. So this is my coroutine, which starts saying hello, and then it waits for some input before it replies with here. All right. So this is half of the picture. This is my coroutine. And in line number 10, I have the function use. That one here in line number 12 calls fun, but this is only a setup of the coroutine. This is getting back this wrapper type, including the promise type, so the coroutine state and the coroutine handle. And the first thing I do down with this wrapper type, you can see it comes with the function listen. We will see that. And so I'm listening to the hello. And then in line number 16, I'm answering into the coroutine, where are you? And then I'm listening again while the coroutine will reply here. So this is the flow of the coroutine. And we can quickly see that in Compiler Explorer. Here we have the output from the coroutine. So this is the hello, where are you? Here. Okay, so this is my coroutine running. But let's now look at the code behind. So the first thing here is my promise type. This is my struct promise type. Imagine it being inside my wrapper type chat. And it comes in line number 2 with the sad part, 2 variables declared in one line, 2 std strings. And I decided I separate them in a message out and a message in. So what goes out of the coroutine and what goes into the coroutine. And now in line number 4, we have our first customization point. Actually, all the rest are customization points. That means we can configure our coroutine and decide what it should do. And we are not going to talk about exceptions during the talk, but the first function, unhandled exception, that leaves us the option to decide what to do if we approach an exception inside our coroutine. And then we have the get return object function. So this is essential. This is what the compiler initially invokes once it sets up the coroutine. And there we tell it what the return object is and how to construct it. In my case, you can see this here in C. We are, of course, constructing a chat object and passing a dis pointer to it. Right? We will see the wrapper type chat on the next slide. And then we have 2 more customization points, initial suspend and yield value, and D and F. And here we can decide what our coroutine initially should do. So once it gets set up, it runs until initial suspend. And this is before it reaches our user code we saw on the previous slide. And here we now can decide, should the coroutine continue running until we hit our user code and maybe the first co-yield return or whatever, or should it pause at this point? And the return type here in line number 6, you can see it indicates with suspend always, that always once we reach initial suspend, our coroutine automatically gets suspended. And this is the same for yield value. And yield value is invoked once we say co-yield. Hence, this function here takes a std_string message by value. You can here freely customize that. You can take all value references, const references, the full picture, okay? Whatever you like to pass from co-yield, it's simply overloadable. You have the option to implement multiple yield values, but I decided to keep it simple at this point. Now, if we look in yield value, then we can see I'm moving the string MSG that gets passed to yield value into my message out variable. And then I return a new suspend always object, which is nothing more than more customization points for the compiler. We will see that. And then in line number 13, I have the await transform. This is when my coroutine awaits some value from the outside. And here it's once again in line number 13, you see the signature. It takes a std_string here, but doesn't do something with it because in my co_await call, I passed an empty std_string. So this is once again just for overload resolution that a compiler knows which await transform function to pick here. And inside this await transform, we see the struct awaiter. And this is more or less what's behind the suspend always, or the other option would be a suspend never. Then the coroutine would continue running after the suspension point. And what I have here is the implementation for suspend always or suspend never. They come with three functions: await ready, await resume, and await suspend. And this gives us even more control and customizability about our coroutine. And in my case, this struct awaiter here stores in line number 16 a reference to my promise type. And then await ready returns true, and await resume, that one moves from the promise type the message in as a return result into the coroutine where we set co_await. Okay, so this is how we get the value out from the promise type, from our message in variable. And I don't do anything in await suspend. I would get a handle of the coroutine here. You will see another implementation where I use that, but at this point I haven't used it. And then I'm returning the awaiter, passing a reference to it, and then the flow runs. And finally, I have return value and always suspend. Return value does return void always, and it's the same for all the customization points that take parameters. We can have different overloads here instead of value, refref, or constref, whatever you want. And here I simply take the message and store it in MSG out. And final suspend, that's called after the coroutine is, or when the coroutine is about to end. And there we can also once again decide, should it continue or should it stop? And it's a wide thing. Usually you want to say suspend always at this point and not fall through to the end of the coroutine. But customization points, you can do that if you have the right application for it. So that's the promise type, which brings us to our wrapper type chat. You can see in line number 2, I include my promise type, and then I do a couple of shortcuts for the handle. Of course, we have a type coroutine handle here, which is typed with our promise type. And I'm shortening that to a name handle. And then in line number 5, I say that chat comes with a member variable and coro handle of this type. And in line number 7, you see the constructor of chat, which takes a pointer to the promise type and calls from promise on this coroutine handle type. This is a static function that's there, and that knows how to convert from a promise type to a coroutine handle, such that I have the ability to control the coroutine later. And because of that handle, you can see it as a pointer. This is something we should not duplicate, because then we have two instances which try to communicate or control this coroutine or destroy it in the end, which is a bad idea. So my coroutine here in line number 8 is move only. I skipped the assignment operation, and it disables the move the copy operations. Okay, so just to be ready here and avoid mistakes. And then the destructor, then I'm checking whether the coroutine handle is still valid, and if so, I destroy it. So we have to keep the maintenance here by ourselves. And then you see the two functions, listen and answer. Okay, listen in line number 17 asks whether the coroutine is already done, and if not, it resumes the coroutine. And after that, in line number 17, it uses the handle and calls the function promise on the coroutine handle, getting back a reference to the promise type, and then it accesses the well-known message out variable and moves that one as a return result out of listen. And then in line number 21, in answer, that one takes a std string message and it moves it into the promise types MSG in. So these are our in and out channels to the coroutine from the complete outside. And then line number 24, should the coroutine not be finished, then we resume it at this point. Okay. So this is our wrapper type chat. And if you look at this, the big picture, then we can see here are on the left our user code. Okay, so this is what we had in the function use. And our coroutine fun returns this type chat. And this is our wrapper type in the middle. And that one contains a promise type. And that promise type may or may not contain additional variables. In our case, it contains 2 std strings, but it's totally implementation freedom for us. And my wrapper type chat, that one comes with 2 methods, listen and answer, which are also optional. It's up to us how we name them, whether we implement them, or whether we do something totally different. And finally, there's the coroutine handle. We use that to resume the coroutine and then put data in and out, but it's also optional. And we'll see later a case where I don't store the coroutine handle because I don't need it. So all are customization points for us. And then on the right, my coroutine handle points to something that's the compiler implementation of a coroutine. So our initial coroutine code, as we write it, gets transformed. You can see that in C++ insights if you wish, but I'm not doing this today. So we have the coroutine, which more or less is a couple of switch cases and storing the values on the heap, on the coroutine frame, which is something that a compiler allocates. You can see below here. And since we don't have any local variables in our coroutine, the coroutine frame does contain only the things the compiler needs to maintain the state of the coroutine, like a suspend index and a couple of other things. So this is this thing in picture. Now, a few definitions. A task is a coroutine that does a job without returning a value, maybe not even using co-yield or co-return. Maybe it uses simply co-await. And a generator, on the other hand, is a coroutine that does a job which returns a value by either co-return or co-yield, because these are rough differences between 2 types. And that's interesting to know because we now will see the different generator types or different tasks types, however you want to call them. But first, one other thing, we talked about that briefly. We have helper types for coroutines in C++. So for yield value, initial suspend, final suspend, co-wait, and await transform, we have the 2 helper types in the standard library, suspend always and suspend never. We saw them in our promise type. And I provided the implementation of 2 below. The only difference between the 2 is that suspend always in its await ready function always returns false, and suspend never in await ready always returns true. Okay, so this is the type. It doesn't store any other information. It implements the await suspend and await resume functions as well, and that's it. So it's just for the compiler to reach into that type, call exactly that function, and then getting an answer whether the coroutine is already ready or should be put to sleep or suspend. So that's the types here, the helper types we have. All right, so that brings us to a task. So we already saw chat. So are you up for another task for coroutine? And that's interleave 2 std vector objects. Okay, so the vision here is I have a std vector with the values 2, 4, 6, and 8, A, and the vector B with the values 3, 5, 7, and 9. And I want to print them out interleaved. And we can do that with a for loop, with using an index, indexing in the 2 std vectors, and then using the the same index, first for the first and then for the second stud vector. Okay, so the output sequence should be 2, 3, 4, 5, 6, 7, 8, 9. And you can also use that as a base for the implementation of a function CP, but I wanted to cut it short at this point. So it's just interleaving. And how do we implement that? Well, we have a new coroutine here, interleaved in line number 1, and that one returns a generator or a type called generator. Remember, this is our wrapper object. And interleaved then takes two stud vectors of int a and b by copy. One thing to note is, because a coroutine can also be returned and later resumed, if you pass in variables by reference or pointers, you must ensure that the data you're passing into the coroutine lives longer than the coroutine itself. Otherwise, you get lifetime issues. So one easy thing is usually to pass in the things into coroutine by copy. Now, inside a coroutine in line number 3, we see another element that can be a coroutine, and that's a lambda. In line number 3 here, I'm creating a lambda lamp, and that one, as you can see at the very end, returns a generator object or generator type, and it takes a stud vector of int by reference. And then in line number 4, you see the usual pattern you so often see with coroutines. I have a for loop or range base for, and I'm iterating over that stud vector. And for each element, I say co-yield. So this is forcing the coroutine, giving the value outside of the coroutine to our caller. So because we have a lambda here, and that means we are giving the value out to the interleaved function. And in line number 7 and 8, the coroutine interleaved now creates two subcoroutines of my lambda lamp for the parameter a and b, calling that one x and epsilon. Now the next thing you very typically see with coroutines, there are often loops in them because they can run forever, because we can pause them and resume them, right? So in line number 10 here, I have a while loop that checks whether either of the coroutines is already finished, or if at least one isn't, we are going into the body of the while loop. So finished here is obviously another function of my wrapper type generator, which we will see next. And then we can see we go into the body, and now in line number 11, we have another if statement that once again checks, oh, is X already finished? No, it's not. Then I'm going in there in line number 12 and co-yielding X.value. So now I'm reaching into the subcoroutine, pulling a value out there, giving it to the caller from interleaved. Okay, so this is the complete way now outside. And after that, in line number 13, X gets resumed. And then in line number 16, I'm doing the exact same thing for epsilon. So we can see our generator comes with the functions finished, value, and resume to make it a little bit more beautiful using this coroutine at this point. So how does our promise type look this time? Way smaller than before. It comes in line number 2, once again with some storage space, an integer this time called val, to store the individual integers of our stud vector, which we want to pull out of the coroutine or hand out of the coroutine. And then in line number 4, we can see for the setup, the get return object. The pattern is the same as before. I'm calling or creating an object of generator of my wrapper type with a different name this time, and I'm passing the dis pointer of my promise type here to the constructor of generator. And I once again have to implement the initial suspend, so this is an always must. And this time I'm saying suspend never. And this is because I have this nested coroutines, and I want the lambdas coroutines to generate a value once they get started. This is why the pattern here is slightly different. And this also illustrates how powerful coroutines in C++ are. You can customize them and adjust them to the behavior you want. So my initial suspend this time says suspend never. So we are always running over this initial suspend until we hit the first, in my case, co-yield from the lambda. And my final suspend, once again, says suspend always. And my yield value this time takes an integer, once again by value, and also says we suspend always. Internally in line number 9, of course, it stores the parameter v into the member variable val from the promise type. And unhandled exception doesn't do anything. So this is my promise type. Very short, right? It's nice. Not so complicated. And here is my generator for the function interleaved. The same pattern, I used the same pattern all over the slides. Line number 2, I'm shortening a handle to my coroutine handle type, creating in line number 3 a member variable in coro handle of type handle here. I have a constructor which takes my promise type as a pointer and calls down on my handle from promise type, getting the coroutine handle from the promise type. It's move only, as you can see in line number 7. It automatically, as I said, disables copy operations. And I'm maintaining that in line number 9 with the destructor that my coroutine gets destroyed once my generator object gets destroyed, my wrapper object. And then you see next the helper functions. In line number 14, I have the function value. So that reaches inside the coroutine handle, inside the promise type, and accesses the member val there. And I'm returning that one. And then in line number 16, I have the function finished, which asks whether the coroutine is already done. And then finally, I have the function resume, which in line number 20 uses finished to check whether the coroutine is already finished. And if not, it resumes the coroutine. So this is all these functions you can see are simply making it better for the caller to have nicer code there. But in the way I have it here with everything public, nothing would prevent the caller from reaching directly in to the coroutine and into that stuff. But as I said, there should be more public and private introduced in real code. So then the functions make even more sense. So and here's how we use them. I have a function use that declares two stud vectors, A and B, with the previously shown values. In line number 6, it sets up my coroutine, the of type generator, call it G, calling the function interleaved and moving the two stud vectors into the coroutine for efficiency purposes. And then you see, once again, a while loop here, where I ask whether G isn't finished. And if not, I'm calling G.value in line number 9. And then I'm resuming coroutine in line number 11 by calling G.resume. So this is interleaving two stud vectors. And you can also zip them. They can have different sizes. It all works. So I think that's a good thing. So the next task then is, I guess we need a plastic surgeon. Because I'm sure we all would like to use range-based for loops instead of the while loop I just showed you, right? At least I would. It's not so nice. So I like the abstraction here. And for this abstraction, I need, of course, an iterator. Okay, so let's make a beautification for our stud vector, for our coroutine. And what do we need for range-based for loop? We have to provide the member functions begin and end for our type generator and return an iterator. And that iterator must fulfill the iterator concept, means it must be not equal or equal comparable in C++20, the compiler can flip there, and it must be incrementable and dereferenceable. Oh, very well, let's do that. You see it here on the right. In line number 1, I create myself a sentinel type, just a tag type, and in line number 3, I implement a real iterator, which in line number 4 stores a coroutine handle. Because it's inside the generator, it can access the alias handle. And then in line number 6, I'm implementing the equal operator, which takes a sentinel. And it takes a sentinel because essentially it only checks whether the coroutine handle is, or the coroutine itself is already done. So it doesn't need the right-hand side object. And then in line number 11, I implement the ++ operation, which returns a reference to the iterator. And internally it calls resume on the coroutine handle and returns a reference to this. And then in line number 17, the dereference operation, what I'm doing here, of course, using the coroutine handle, accessing the promise type, reaching for value. So that's my abstraction here. This is my iterator implementation. It's also very nice thing, small code. And here then I have to add the begin and end functions to generator. Begin returns an iterator, end returns my sentinel. In begin, we can see I'm passing the coroutine handle to my iterator. And now I can modify my code in function use, as you saw it before. We have in line number 1 and 2 below here the two state vectors. Line number 4 sets up the generator. And in line number 6, I have the range-based for loop now, which I use with my generator, looping over the generator and simply using E here together with std out. So I don't see that a coroutine is behind that. So it's a nice abstraction, okay? Makes using them really nice. But you can, of course, decide what to do. You can go for both implementations. That's the beauty here in coroutines. All right, that's interleaving two state vectors. There's another thing. Scheduling multiple tasks, right? I talked about multi-threading, cooperative versus preemptive multitasking. So how would that look like with coroutines? Cooperative multitasking. So let's say we have the following. We start with the function use. That has or creates in line number 3 a scheduler object. Call it scheduler. We see later what scheduler looks like internally. But it's a scheduler, a really nice one. And then in line number 5 and 6, I create two tasks, A and B, passing scheduler here. And we can see that task A and task B don't return anything, or at least we don't take it. They do. They are coroutines, but this time we are not interested in this wrapper time, in maintaining a reference to it. And then in line number 8, we call scheduler.schedule. So schedule the two tasks. You can easily extend it, having multiple tasks, but I think for the purpose of this talk, two tasks are fine. They are enough. How do my tasks look like? These are my tasks. I have a task A and a task B. They both take a scheduler by reference. And internally, they use cout to simply say hello from task A and hello from task B. Very simple. The interesting thing is in line number 5 and 9, they suspend themselves by calling cowait on sched.suspend, our scheduler. And we will see the implementation of that. But this is where the coroutine gives up control, gives control back to the caller. And this is the cooperative part here. Our coroutine can run up to a certain number of instructions. If you know your architecture, your program very well, you can pin a time on that and can say, okay, 5 instruction equals, I don't know, 5 milliseconds. So I let my coroutine run for 5 milliseconds, then it gives up control, and later it gets resumed, can be run for another 5 milliseconds, and so forth. So you can do a very precise scheduling if you know enough details about your system. But you have even more control even without knowing that, because you know the exact points when your task gets interrupted. And you can ensure that, say, while transferring data, you don't get interrupted because you don't co-wait at this point. So this makes coroutines real nice for these tasks. So this is the two tasks. As I said, the only difference is the one says A, the other one says B. You can put in, of course, more meaningful code for you, like reading a file, writing a file, all that stuff. And as we've seen, these operations can be coroutines themselves. So everything can get more coroutine at this point. Now looking into the scheduler, this is the implementation of scheduler. It's a real cheap, easy one. It uses a stud list in line number 2, storing a bunch of coroutine handles. And these are handles of type void, because we are not interested in the wrapper type. We only want the promise type. The promise type is always called promise type. So then in line number 4, we have the function schedule. And that one simply pops the first coroutine handle out of my task list and checks in line number 9 then, is my coroutine already done? If not, it gets resumed. So the task gets resumed. And then we are there until the task gives control back to us. And then the result of schedule is it checks whether the entire list of coroutine handles is empty. That means there is nothing more to schedule. But every time we schedule, we pull one element out of our list. And then we have the other function, suspend. And suspend now uses a similar pattern we saw before with await transform. In line number 16, I'm creating my self-destruct awaiter. The name here, by the way, is optional. It's just a name. It's not like the promised type, which must be spelled exactly like that. And this time I took the liberty to derive from suspend always for my awaiter. And internally, my awaiter stores reference to the scheduler. That means it needs a constructor here in line number 19, storing or setting this reference. And then the only thing I'm overriding from suspend always in line number 20 is await suspend, because this time I'm interested in the coroutine handle once the coroutine gets suspended. Because what I'm doing here, I'm using the reference to my scheduler and pushing back this coroutine handle to the list of tasks. And by that, when I schedule, I pull one out, and when the coroutine suspends itself, it can push itself back into the task list. So this is how the system works, pulling one out, putting one in. And then await suspend in line number 23 returns the awaiter, which is essentially a modified suspend always version. Okay, and because we are not reaching for base classes here, overriding this function without being virtualless is fine in this case. It saves me a lot of slide space at this point. So this is the scheduler. This is your tiny little scheduler. You can tune that and do more awesome things. And you can have multiple schedulers if you want, whatever. So this is your base for scheduling multiple tasks with coroutines. And now here is my promise type and my wrapper type task. And this time it's really thin because I only need a wrapper type to contain the promise type. My wrapper type is not interested at all about anything belonging to the coroutine. It's simply the carrier for the promise type. It doesn't store anything. And my promise type internally, as before in line number 3, says, okay, we are creating with get return object such a task object. It's empty, constructed as a default constructor provided by the compiler. And then in line number 4, I have my initial suspend, which once again says suspend never, because I want to run my task directly. But that's up to you. You can also decide that your task always gets paused. This would be also a point where you can execute code when your task gets started, registered it somewhere or whatever. And then final suspend also says suspend never. This is one of the cases where I don't want that because my task essentially ran forever. And then in line number 6, unhandled exception. As before, I don't care about exceptions at this point, so this is fine. So this is my task type at this point. You can see it way less customization points required for this one. And you have a basic system where you can schedule tasks. And you don't need any threading. You can add multi-threading to that, std threads or anything like that, but you don't need it. You have full control at this point. And that's really worth something. However, just to show you that, you can also say you want to modify your implementation. And the coroutines or your tasks shouldn't know about a scheduler. So another implementation would be in line number 3 and 4, task A and B are still my coroutines. I don't care about the wrapper type, about the return value from task A and B, and I don't pass any parameters to them this time. And then in line number 6, you can see why I now have a global object, gscheduler, and call schedule on that one. So let's see how the implementation changes using this approach. My task A and B looks slightly different. Of course, they don't take a parameter anymore. And in the co-await calls in line number 5 and 9, you can see I'm calling co-await now on a new object I create all the time, suspend. So it's obviously also a new type. You can pick any name here. I thought it would be nice to say suspend at this point. My scheduler implementation changed also slightly. I still have a std list of coroutine handles, but now in line number 4, I also have a function called suspend. That one takes a coroutine handle and calls pushback on my std list, pushing that coroutine handle back to the list. And then in line number 6, my function schedule, that's the same as before, pulling one coroutine handle out of the list, resuming it if it's not already done, and then returning whether the list is already empty or not. And then finally, I have in line number 1 a global object of static storage duration called scheduler, gschedule, and my struct suspend in line number 3 to 12. And that one implements a new operator, the co-wait operator. So there's not only the keyword co-wait, we can also have a corresponding operator. And once I call co-wait with a type, the compiler also checks whether this type comes with a co-wait operator. So this is how we reach inside that. And you can see the same pattern as before. I'm creating myself the struct awaiter in line number 6, and it derives once again from suspend always. This time it's even simpler because there's the global object. I don't need to store reference inside this awaiter struct. So all I have to do is to override the await suspend function from suspend always, saying, yes, I take this coroutine handle, and I'm calling gscheduler.suspend with that, passing the coroutine handle there. And I'm done, right? That's nice. So here's the demonstration in C++ in Sites. You can luckily, meanwhile, use coroutines in Clang and in GCC. The only thing you have to keep in mind that together with Clang, I think even with the latest release, you have still to use the libc++ as the standard library, on Linux at least. And for GCC, I think you have to enable an option like coroutines to enable coroutine support there. But here now we have a running version with Clang. You can see here, this is my task implementation. This is the scheduler implementation as we had it before. We have the 2 tasks here. So this is still the version where you pass the scheduler into the coroutine or into the task. And then you can see the output here. First, hello from task A, then hello from task B. A is doing work, B is doing work, A is doing more work, and B is doing more work. And then I'm done. Program is finished. And this is a real, as I already said, real simple scheduler. You can extend it, you can modify it, but this is what you can do with coroutines, just as a couple of insights what you can do and how the things relate to each other. All right. So coroutines, and as I said, there are other talks available where you can check out different explanations, I think, for the same systems. You saw a little bit of the customization points in our promise type. We talked about preemptive and cooperative multitasking. So this scheduling system here is all preemptive. You don't get interrupted if you don't want to. You, of course, can mix that with std threads, but then things once again get more complicated. But it's entirely possible. Okay. So yeah, I didn't properly introduce myself this time. So my last name is Fertig. It's a German name which you can translate in English to finished, complete, or completed. A real nice name. If you're interested more in coroutines, I just put up a coroutine cheat sheet which visualizes the chat coroutine we saw in the beginning a little bit more, pinning the code to the individual customization points. Just you can see better how they relate, how they connect to each other. There's also a flow chart in there which illustrates the different states a coroutine comes with and is into. And there is a table summarizing the different customization points and where to put them or where not. If you're interested, you can also read more about coroutines in my Programming with C++ 20 book. Yeah, and at this point, I can only refer to my name and can say, I am Fertig. Thank you. And now it's time to take your questions. So what do you see here? Not a comment, not a question, but a comment. It depends on the implementation and even runtime state if co-wait and co-yield actually suspend the coroutine. Yeah, I think we covered that. That depends on the return type from the co-yield or from the yield value or initial suspend. So there you can configure that by saying either suspend always or suspend never. And Phil says, worth mentioning that there is a stud generator in C++23. That's right, Phil. Yeah, thanks for pointing that out. I think we got it very last minute. So you don't have necessarily to write all the generator code, but I haven't had the time to look deeply into it and see how that changes a lot of my implementations. But that's, of course, a good thing. There's library parts definitely missing. So then we have on slide 27, thanks for the reference. On slide 27, there is a confusion that the task type is empty and it couldn't remember what was responsible for Coro frame and promised live state. Can you maybe over how that worked? So if I understood the question right, Donnie, then the task here isn't really, it's just a carrier for the promise type. It doesn't maintain its state because we assume that our task never finishes. You can also have a different implementation where you say, yeah, if my task finishes, I at least provide a constructor and a destructor. I need a constructor to get a coroutine handle during construction and the destructor when my task object gets destroyed to be able to also free the coroutine. But the vision here from me was that I have this model of tasks where the tasks simply run forever, or at least as long as the program runs. And once you finish the program, the operating system will free all your memory anyway. So this is the short version here. You can do a more elaborate version if you say my tasks get set up and they end and I set up a new one and they end. So this is something you can do at this point. So and then another question, what are the most common pitfalls of using coroutines in already multi-threading environment? Should I expect more cache misses, for instance? So if I understand this question right, you're saying you already have multi-threading, and now I'm not sure whether you want to add coroutines into that mix or replace your threading system with coroutines. So I'm not really sure how to answer that at this point. Well, it's hard to say whether you have more cache misses. The coroutine frame is stored on the heap, so there is a potential that this is not in the cache when scheduled next, such that it has to be pulled into a cache line. That's of course possible. From the data arrangement in there, the data in the coroutine frame is perfectly aligned, I would say, in the order you declare the variables. So that should not be an issue for caching. The one thing I pointed out is be sure that you pass either by value or that your objects you're passing to your coroutine live longer than the coroutine itself. So you can create yourself a similar situations like with lambdas, where you have a lambda that captures by reference and you return that one. And the reference it just captured was something on the local stack from the function. And this is essentially the same with coroutines, creating a coroutine inside one function, passing a couple of parameters by reference, and then returning that coroutine would result in the same thing. Other than that, I don't know any pitfalls immediately, but feel free to reach out to me either via Discord or via email, Twitter, whatever, and maybe explain a little bit more what you have in your mind, and maybe I can give you a better answer then. All right, and one more question popped in. What are the requirements in current compiler implementation to enable heap elision? Oh, that's a real good one. It was too much for this talk. Let's phrase it that way. There are ways to enable the compiler to get heap elision. Of course, they do the usual things, so they might be able to do that without us doing anything special if the coroutine looks, simple enough to them. If I remember correctly, on the Clang mailing list, they were also discussing more scenarios where they can apply heap elision, but I'm not really certain about that. And there is another way, which Gore showed me, how you can enforce heap elision. At this point, it's in my book, but it's too broad now to put it out there. But there are ways. Let's phrase it like that. And same as before, feel free to reach out to me, and I can send you more information about that. Perfect. All right. All questions answered. Thanks for your questions. Thanks for your time. I hope you enjoyed it. And check out the other coroutine talks we have here at CppCon. And maybe you also want to check out my talk on move semantics later, but that's nothing to do with coroutines, right? So enjoy CppCon. Have a lovely rest of your day, and maybe we see each other once again in the future. Bye-bye.